Welcome. We often see computer vision as a black box that magically identifies objects in an image. But for those of us building, deploying, and relying on these systems, magic isn't a scalable strategy. Today, we're going to peel back the layers and move beyond the pixels into the core mechanisms that enable a machine to see. We won't just rehash the basics of a convolutional layer. Instead, we'll trace the evolution of thought, from the rigid logic of handcrafted features to the learned hierarchical representations of CNNs, and finally to the global context-aware reasoning of vision transformers. The goal here is to arm you with a deeper intuition. For engineers, this means understanding why a model fails. For architects, it's about choosing the right tool for the job. And for data scientists, it's about knowing what happens when you move beyond the model.fit command. Let's begin. Before deep learning dominated the landscape, we had to tell our algorithms exactly what to look for. This was the era of handcrafted feature descriptors. Think of algorithms like SIFT, Scale Invariant Feature Transform, or HOG, Histogram of Oriented Gradients. These weren't learning algorithms in the modern sense. They were brilliant, engineered pipelines based on human intuition about vision. For example, SIFT identifies key points in an image by finding locations that are stable across changes in scale and rotation, and then describes the neighborhood around each key point using local image gradients. It's essentially creating a robust numerical fingerprint for a patch of an image. This approach was powerful because it encoded our prior knowledge that corners and textured regions are important for recognition. However, its core limitation was its rigidity. These descriptors are brittle. They struggle with significant variations in lighting, occlusion, and viewpoint that weren't explicitly encoded in their design. This foundational understanding is critical, as the core idea, finding hierarchical features, is precisely what neural networks learn to automate. The paradigm shift came with convolutional neural networks. The genius of the CNN wasn't just in its performance, but in its philosophy. Stop telling the model what to look for and let it learn the features itself. This is where the real deep dive begins. A convolutional layer isn't just a filter, it's a trainable feature detector. In the initial layers of a network like ResNet, these filters learn to activate on primitive patterns. Oriented edges, color gradients, simple textures. Think of them as a massive, optimized bank of Gabor filters. As we move deeper, the magic happens. The second convolutional block doesn't see pixels anymore. It sees the output of the first block. Its input is a rich map of where the simple edges and gradients are. So its filters learn to combine these primitives into more complex concepts: corners, simple curves, or repeating textures. Deeper still, layers might learn to combine corners and curves to detect an eye, a wheel, or a keyboard key. This is the essence of hierarchical representation. The network isn't just learning what a cat is, it's learning the entire visual vocabulary needed to describe a cat, from the texture of its fur to the shape of its ear. This spatial hierarchy, preserved through convolutions and downsampled through pooling, is the core architectural insight that made deep learning work for vision. For years, CNNs were the undisputed champions. Their inductive bias, this idea of local connectivity and spatial hierarchy, is a powerful prior for how images work. But what if that bias is also a limitation? A CNN kernel has a limited receptive field. It can only see a small patch of the image at a time. It struggles to understand long-range global relationships. Enter the vision transformer, or VEAT. Borrowing directly from natural language processing, the VEAT takes a radically different approach. It slices the image into a grid of patches, say 16 by 16 pixels each, and treats them like words in a sentence. These patches are then fed into a standard transformer architecture. The key mechanism here is self-attention. For any given patch, the attention mechanism can dynamically calculate an importance score relative to every other patch in the image. This allows the model to learn long-range dependencies from day one. It can learn that a patch corresponding to a boat's sail is highly related to a patch of water at the bottom of the image, even if they are far apart. This is something a CNN has to learn implicitly through many layers of pooling. The trade-off? VEATs have a weaker inductive bias, which means they are incredibly data hungry. But on massive data sets, their ability to learn global context without being constrained by local receptive fields often leads to state-of-the-art performance. For an MLE, this choice, CNN versus VEET, is a critical decision about the trade-off between prior knowledge and data scale.
So, we've journeyed from explicit handcrafted rules in SIFT to the learned local hierarchies of CNNs, and finally to the learned global relationships of vision transformers. Each step represents a higher level of abstraction and a greater reliance on learning representations from data rather than engineering them. The key practical takeaway is this: there is no single best architecture. The choice is a complex trade-off. CNN are data efficient and great for problems with strong spatial locality. VITs excel when you have massive scale and need to model global context. Understanding this fundamental difference is what separates building a model from engineering a solution. The future is moving beyond simple recognition towards true multimodal scene understanding, where vision is just one input into a larger reasoning system. Thank you.